Hello guys, and welcome to another calculus video. In this video we are starting the infinite summation guide. So this is going to be a 3-part series. It may be 4 parts now that I'm noticing that I'm missing some things that we need to go over. And essentially this guide is going to prepare you to evaluate pretty much any straightforward infinite sum. We're going to stick with mostly single infinite sums, so we're not going to dip too much into double summation unless it's to evaluate a single infinite sum. And in this video, we're just going over the basics that you're going to need in order to start learning how to evaluate these sums. So, without any further ado, let's go ahead and get started on the video. So, in this section, this is part 1. You may be watching this as a full series, or you may be watching it in separate videos. In this section, part 1, we're going to be talking about basic series manipulation, the geometric series and its derivatives, the common power series that we're going to need to know, binomial power series, application of known series to summations, and cumulative practice problems. The only prerequisites you need for this series are you need to know basic series convergence tests basically at the calculus BC level, and you also need to know what a Taylor series is, which isn't actually as important. So first we're going to talk about basic series manipulation. So one of the manipulations that we're going to be using quite often is changing indices. So changing the index of a summation can prove very helpful in many situations, whether it's to convert a summation into a known power series or simply to make evaluation simpler. So I'm going to go over a really straightforward example. If we have the sum from n equals 23 to infinity of 1/2 to the n minus 23, obviously those 23s are kind of in the way, and though we can evaluate it in this form, it's going to be easier if we could start at 0 or 1 rather than starting at 23. So what we want to do is shift it over so that instead of n starting at 23, we have some other variable. Usually I will just use n again, but for the purposes of this example, I switched it to a different variable k. So as you can see here, we know that we want to start when n equals 23, or when n minus 23 equals 0. So we know that n minus 23 is going to be 0 for the lowest term in this summation. So if we want our summation to start at 0, we can just set another variable k equal to n minus 23, because then when n minus 23 is 0, k is also 0, and that's our first term. So essentially what we do is we take the equation at the lower bound of the summation here, n equals 23, we solve, we put everything on one side, and then we set a variable equal to everything on that side, because then we start at 0. So here, our variable here, k equals n minus 23. So we're going to be starting at k equals 0, and this is a plus sign, but this should be a minus sign right here. Because since k equals n minus 23, when n equals infinity, we could say, quote-unquote, k is 23 less than infinity, right? Since k equals n minus 23. But of course, since we're going to infinity, it doesn't really matter overall. We're still going to be going all the way to infinity. And notice we replaced n minus 23 with k right here. So we just end up with the sum from k equals 0 to infinity of 1/2 to the k. Here's another example right here. We have a summation from n equals 1 to infinity of f of n plus 2 times g of n minus 2. And we're saying that in this case, rather than shifting our variable to make our summation start at 0, we're shifting our variable to make our summand a little bit simpler, because instead of having f of n plus 2, we want this to be f of k. So this is a little bit easier because we just say, okay, well n plus 2 is going to be equal to k, which means that k minus 2 is equal to n. So when n equals 1, which is the lower bound of our summation, we just plug in k minus 2 equals n. So k minus 2 is equal to 1, and k is going to be equal to 3. So that's the lower bound as well. And again, we don't have to change the upper bound because that's just infinity. Subtracting or adding 2 isn't going to affect it. And notice we also had this function g of n minus 2. And so in order to substitute that in, all we have to do is again just replace n with k minus 2. So we just end up with the sum from k equals 3 to infinity of f of k times g of k minus 2 minus 2, which is just k minus 4. And that's our new summation right here, which should hopefully be a little bit simpler to evaluate. Alright, let's talk about separating summations. So with a finite summation, separating summations is very, very easy. We just separate the sum from n equals a to b of f of n minus g of n equals the sum from n equals a to b of f of n minus the sum from n equals a to b of g of n. However, when we're going to infinity, or I guess you could say we take the limit as b goes to infinity, we do have to follow some other rules here, because if we separate these two summations, but both of them diverge, then that just doesn't work out. I mean, we can't say that infinity minus infinity is equal to, some finite number. So as long as both of these outside series do converge, then we can make this statement right here, that the sum from n equals 0 to infinity of f of n minus g of n equals the sum from n equals 0 to infinity of f of n minus the sum from n equals 0 to infinity of g of n. So whenever you're making this split, make sure that your summation will still converge even after splitting it apart. And in part 3 of this series, we will go over a way that we can actually get around this rule and sort of split up these summations. Even if they diverge, so that's going to be cool. Exchanging the order of summation. This is not something that's going to be helpful to us for the first video, but it is something that is probably important to cover early on, since it is a fundamental feature of summation. So if we have a summation, a double summation, where we're taking the sum from n equals 0 to infinity of the sum from k equals 0 to infinity of some term right here, which is dependent on both n and k, we can go ahead and flip the order of summation here, so that we sum with respect to n first, and then we sum with respect to k. However, we do need some justification in order to do this, and this is using Fubini's theorem, which you might remember from some of my integral videos. It's essentially the same theorem, except instead of using integration, we're using summation. So this will only work if we take the original summation and we throw absolute value bars on each term if it still converges. If it still converges, then we can go ahead and exchange the summation, and that's great. If it doesn't converge, then we might not be able to switch the summation. So I'm going to be honest, I have most definitely violated this rule before, and that's not something good. That's not something you should be doing in general. So in general, it's not safe to do this if the absolute value does not converge, but in some specific cases, it may work even if the absolute value does not converge. For the most part, we're going to be dealing with summations in which this rule, which is called Fubini's theorem again, is satisfied. And in most cases, honestly, this a and k will be positive anyway, so taking the absolute value won't change it at all. So now let's talk about our most important infinite series. So my approach to this video is going to be presenting you with as many infinite series as possible, because when it comes time to solve an infinite summation, the only real way to solve these kinds of problems is to make that summation look like another summation that you already know. So if you know lots of different generalized summations, you'll be able to evaluate a lot of other different summations. So the most important one by far is the geometric series here. So this is 1 over 1 minus x is equal to the sum from n equals 0 to infinity of x to the n. This, the radius of convergence here, which is pretty easy to calculate, says that absolute value of x has to be less than 1. Using this summation, we can actually get lots of different useful infinite series, and we can do this using integration and differentiation of power series, which we're going to go over right here. So differentiating and integrating power series is actually really interesting, because this is one of the cases where the justification actually isn't very difficult. So let's say we wanted to take the derivative of this infinite summation, the sum from n equals 0 to infinity of an times x to the n. Well, that's actually just the same thing as taking this derivative and putting it on the inside of the summation, in which case we get n times x to the n minus 1. Notice that I changed the index here from n equals 0 to n equals 1. Can you think of why I did that? Well, when we differentiate, that first term was an x to the n, where n was 0, so it was just a0, which was just a constant. And when we differentiate with respect to x, constants just disappear, right? So that's why we have to make sure to remember to remove that first term before we do anything else. If you don't remove the first term, it's not a big deal, because this n is still going to be 0. But if you go ahead and differentiate again, and you still forget to remove that first term, it can sometimes become a problem. So the interesting thing here is that, again, I said you can just put that derivative on the inside, and this is gonna work in every situation as long as you remain within the region of convergence. You could also do the same thing and integrate term by term, which means that the sum from n equals 0 to infinity of an x to the n equals the sum from n equals 0 to infinity of an x to the n plus 1 over n plus 1 plus c. So something that's very, very useful in this situation is if I have some sort of summation that looks sort of like a summation that I know, which is equal to sum from n equals 0 to infinity of a n x to the n. However, this other summation has an n plus 1 on the bottom, so that means it's not the same as the infinite series that I already know. However, we can go ahead and use this rule right here, and we can rewrite sum of a n x to the n plus 1 over n plus 1 as the integral of a n x to the n. And again, there's no sketchy rules here. You can integrate and differentiate term by term as long as you remain within the region of convergence. So let's look at some examples of how this is useful. In terms of integration, if we take the geometric series and we integrate with respect to x, we get that negative natural log of 1 minus x equals the sum from n equals 0 to infinity of x to the n plus 1 over n plus 1 plus c. And setting x equal to 0, we find that c is also equal to 0. And this gives us two very important infinite series. The sum from n equals 1 to infinity of x to the n over n equals negative natural log of 1 minus x. And if we go ahead and add a negative 1 to the n plus 1 in there, it becomes natural log of 1 plus x. Also, if we differentiate the geometric series, we find that we get 1 over 1 minus x all squared on the left side here. And when we differentiate on the inside, we get the sum from n equals 1. Again, we shift the index over by 1 because that first term is going to disappear. N equals 1 to infinity of n times x to the n minus 1. And you can actually repeat this process as many times as you like. So if we assume we repeat this process k times, you're going to find that you're going to get, on the right side here, sum from n equals k to infinity of n choose k. That's a combinatorial, which will, I have the expression for it over here. N choose k, x to the n minus k, and this is equal to 1 over 1 minus x raised to the k plus 1 power. And n choose k just means this right here. It's going to be n times n minus 1 times n minus 2, all the way down to n minus k plus 1, and dividing by k factorial. So this is really helpful because if we ever have anything that looks like a combinatorial here, we can express it as just a power of 1 minus x. Also, if we have any polynomial in n times a power of x, then we can rearrange that polynomial into expressions in terms of n choose k, and then figure out the summation from there. So I'll go over an example of that in a moment. So all of these series are instrumental in solving many infinite summations. Let's look at some examples of their use. So here's an example right here. We have the sum from n equals 1 to infinity of sine of n over n. Now, proving the convergence of this is a little bit difficult. You have to use a test called Dirichlet's test, which is not taught in Calculus BC, but for now, we'll just assume it converges and calculate the value here. So we're going to use, of course, the sum from n equals 1 to infinity of x to the n over n equals negative natural log of 1 minus x. So what this is going to look like is, right now we have sine of n over n rather than x to the n over n, so we have to figure out how to write sine of n as a power. And the way to do this is we write sine of n as the imaginary part of e to the in. So we have the sum from n equals 1 to infinity of the imaginary part of e to the in over n. And if you think about it, if you take the imaginary part of a bunch of numbers and then add them together, it's the same as adding together those numbers and then taking the imaginary part. So we can bring this imaginary operator outside. And that means that we just have the sum from n equals 1 to infinity of e to the I, all raised to the n power. And then we just apply this rule right here. So we get the imaginary part of negative natural log 1 minus e to the I. Substituting in, we get negative natural log of 1 minus cosine 1 minus I sine 1. Then, using the rules of complex natural logarithms, we get tan inverse of sine 1 over 1 minus cosine 1. And after some trig identities, we get pi over 2 minus 1 half. And that was super straightforward, just using directly this rule x to the n over n, summed up from n equals 1 to infinity. So whenever you see anything with a power and then some n or some rational function in the bottom, you're immediately going to think of using this series right here. Here's an example of a different situation. So here we have the sum from n equals 1 to infinity, and instead of having n on the bottom, we have n on the top now. And it's actually n squared, and we're multiplying by x to the n. Well, whenever we see a polynomial of n multiplied by x to the n, we're going to use the sum from n equals k to infinity of n choose k, x to the n minus k equals 1 over 1 minus x raised to the k plus 1 power. Now notice that we have a power of 2 right here. Now when you have n choose k, the power of n choose k is always going to, the highest power, sorry, of n choose k is always going to be k. So if we want to get an n squared, we're going to choose k equals 2. And when we calculate all of that, we're going to get that the sum from n equals 2 to infinity of n squared minus n over 2 times x to the n minus 2 equals 1 over 1 minus x cubed. And notice here I multiplied by 2x squared on both sides just to make everything a little bit more straightforward. And also, notice that here we get n squared minus n, but we're just looking for n squared. So we need to add back one of those n's, and we are able to do this by choosing k equals 1. So for k equals 1, we get this summation right here, and in order to get rid of this minus 1, we multiply by x on both sides. Now, notice we have the sum from n equals 2 to infinity of n squared minus n times x to the n, and the sum from n equals 1 to infinity of n x to the n. Now, something important to note here is that the sum from n equals 2 to infinity here is the same as the sum from n equals 1 to infinity, because if we plug in n equals 1, we just get 0 in the summand here. So we can rewrite this as the sum from n equals 1 to infinity. Then, when we add these two summations together, we can just go ahead and combine them, and we get n squared minus n plus n, which is just n squared. So we get our original summation that we were looking for, sum from n equals 1 to infinity of n squared x to the n, which was equal to 2x squared over, well, I won't go over this, but you just simplify and you end up with this expression right here. So, tips for using these two series: whenever you have x to the n combined with rational functions of n, look to use that series with natural log 1 minus x. If the denominator is shifted over by 1, so for example, if you have x to the n over n plus 1, first you want to shift the index so that it matches the original series, and then you want to factor out any extra terms. So in the example of sum of, I'm going to just write this right here, if we have the sum of x to the n over n plus 1, once we shift the index, we're going to end up with the sum of x to the n minus 1 over n, right? And so then we just factor out an x, and then that minus 1 will disappear, and we just have the sum of x to the n, and that's easy to evaluate. Whenever you have x to the n multiplied by a polynomial of n, you want to figure out how to write this polynomial as a sum of n choose k for different k, and apply the known series, which is exactly what we did in that example right there. And the first thing you're going to want to do when using this strategy is figure out what the order of the polynomial is, and that tells you what the highest value of k is that you're going to need. So now let's go over some other common power series that are going to be very, very useful in evaluating infinite series. Some of these are derived using Taylor series, while some of the other ones come from the geometric series. So from Taylor series, we have power series for e to the x, cosine x, sine x, hyperbolic cosine x, hyperbolic sine x, and all of these can just be proved using the definition of a Maclaurin series. Now, I'm not going to prove them right here because they're relatively straightforward to do, but they're just good to have in mind. It's not a problem if you want to have a table of these around while you're starting to solve problems, just because it's hard to memorize so many infinite series, right? But as you use these series more and more, trust me, you'll be able to memorize them eventually just through practice. From the geometric series, we have power series for inverse tangent of x and inverse hyperbolic tangent of x right here. And inverse hyperbolic tangent of x is the same as 1/2 times natural log of 1 plus x over 1 minus x. So there are also some power series which come from the binomial expansion, which I'm not going to go over here, but just know that it's 1 plus x to the k equals the sum from n equals 0 to infinity of k sub k choose n times x to the n. One thing to note here is that if k is an integer, then this series here, or is a positive integer, sorry. If k is a positive integer, then this series here will go on for a few terms, and then every term after that will be 0. So it's actually the same as a finite summation. So for example, if k were equal to 2, then we know the left side is just 1 plus 2x plus x squared, and so the right side would end up being the same thing. But if k is not an integer, like for example 3/2, then this right side will go on forever. Something else to keep in mind is a series that will often show up, or a function that will often show up, n double factorial. this is equal to n times n minus 2 times n minus 4, all the way down to 1 if n is an odd number, and all the way down to 2 if n is an even number. Now, I don't have them in here. You can replace these definitions for the series for 1 minus x to the negative 1 half, or sine inverse of x. You can replace some of this with double factorials, but I'm not going to do that for now, just because I think they're going to be a little bit more useful just using factorials. So these series right here look really nasty, but essentially they just come from plugging in k equals negative 1 half and replacing x with negative x in the binomial series here, and then simplifying this this k choose n where k is negative 1 half. And then this inverse sine series just comes from integrating this one once you replace x with x squared. So for these two, I would say you definitely don't have to memorize them, but know that when you see this pattern of 2n factorial over n factorial squared and 4 to the n on the bottom, you're probably going to have to use one of these two series, and you can go look them up. So something really important to know is that using series with differentiation and integration is the main way that we're going to end up creating new series. So for example, if we have a series that looks similar to a known series, but with an extra factor of n on the top or bottom, we can either differentiate or integrate the original series to make it look like the known series. So first of all, ignore all the colored stuff here. I'm just going to go over the stuff that's in white. So we have the sum from n equals 0 to infinity of negative 1 to the n times 1 half to the 2n plus 1 over 2n plus 1 times 2n plus 2, and this is our sum s. Now, we notice that this looks really, really similar to the series for inverse tangent of x, which is this right here. The only difference is that there's a 2n plus 2 on the bottom here. Well, we think, okay, how could we get a 2n plus 2 on the bottom of something? And a good way to think about this is it happens when you integrate x to the 2n plus 1. Because when you integrate x to the 2n plus 1, you get x to the 2n plus 2 all over 2n plus 2 plus some constant c. So what we're going to do here is if we just integrate this original series from 0 to 1 half, notice what's going to happen. Well, when we integrate it indefinitely, we're going to get x to the 2n plus 2 all over 2n plus 2, right? Then when we plug in 1 half, for the upper bound, we're going to get 1 half to the 2n plus 2, which is exactly what we're looking for, except this is 2n plus 1 right here. And when we plug in 0, that's just going to be 0. So when we integrate this, I'm not going to go over the integral of arctangent because you guys should know that, but that's what this is right here. And then on the right side, we're going to get the sum from n equals 0 to infinity of negative 1 to the n, 1 half to the 2n plus 2 all over 2n plus 1 times 2n plus 2. And that's exactly what we want right here, except there's a 2 in the exponent here and there's a 1 right here, so this is actually equal to s over 2, which means that our original summation s was just equal to inverse tangent of 1 half minus natural log of 25 over 16. So some other tips for using power series right here. You can use partial fractions to make some summands simpler. Now this is going to become much more important in our next video, but in general, partial fractions can make really complicated looking things looking a lot simpler. For example, in this summation up here, if we used partial fractions instead, we would get one term that turned into an inverse tangent and another term that turned into a natural log. And so that's also a perfectly good way to solve this problem. However, once you see that 2n plus 2, it is also easy just to integrate. Another thing to note, practice makes perfect. The only way to solve these types of problems is to recognize the power series, so don't worry if you get it on the first try. Once you get more used to solving these types of problems, you're going to be able to notice, oh, that's this power series, and then be able to solve the problem from there more often. So, you know, your first few problems you're probably not going to do too great on, which is why I try to make them a little bit easier. Shifting indices is often going to be very, very helpful to make the series more recognizable. So if you see a series that looks shifted over by a certain amount, like maybe it has n plus 5 in the denominator, try shifting it over first, and then seeing if it looks like anything that you're familiar with. And then, of course, learn as many power series as you can, because every problem is going to relate to the power series of some function. I find the best way to remember power series is to try to figure out how to derive them all, because it's a lot easier to remember a derivation than some random formula that you have no idea how it works. And if you completely forget the formula, you can just derive it again, which in the case of the functions that we're talking about is generally not that difficult. So let's try some practice. Go ahead and try to evaluate the following summations. At this point, I'm also going to say, if you need any help with these problems or you want some, extra help, feel free to join the Discord, and I'm happy to help anyone who needs some help. So if you're not able to solve these, yeah, that's definitely an option. Alright, so hopefully you were able to figure out all those summations. We have some more practice right here. Alright, so hopefully you were able to figure out all those problems. If not, feel free to join the Discord and I can help you out. And that's it for this video. If you guys, thank you guys so much for watching, and I hope to see you in the next one. In the next one, we're going to be going over summations of rational functions. We're going to be talking about zeta functions, eta functions, digamma functions, and polygamma functions as well. So that's going to be a lot of fun. Hope to see you in that next video. I hope you enjoyed this video, and I'll see you next time. Thanks. Bye.